Well, good morning, everybody, and welcome to the February edition of the ABA Engineering Academy's engineering webinar. We hold these webinars each month on the third Tuesday, and we try to have some very interesting guests from time to time to talk about things that are of interest to broadcast engineers and also to those that are involved in the pro audio field as well. We seem to find out that there's a lot of broadcast engineers that also are involved in pro audio, especially mixing audio at their churches and maybe working with bands or other organizations. So we try to have some stuff on that as well. Uh, this particular seminar today, a webinar, is actually sponsored by our good folks at RF Specialties South, and they can furnish anything you need for your radio station, anything from a microphone all the way up to the beacon on top of the tower. And John George, our good buddy with RF Specialists, normally is with us, and but I think I talked to him earlier this morning. He's on the way to Nashville, getting ready for the National Religious Broadcasters Convention being held in Nashville, but he's sort of stuck in traffic in the Smoky Mountains, traveling over from South Carolina. And apparently there's a lot of road damage up there because of storms and snow and ice and all that. So he wasn't sure he was going to be able to be with us, but he said if he was, he'll just jump on as he goes along. Today, we've had quite a few discussions about uh, AM and yes, Virginia, this still is AM radio stations, and they'll be around. They're not going anywhere. But there's a lot of confusion sometimes about different things that take place in AM, especially in how to maintain the correct power output of your AM facility, how you measure it, and especially when it comes to non-directional, the things that you need to do. So I decided I'd contact the AM guru for the United States, my good friend Cris Alexander with Crawford Broadcasting. Chris, thank you for joining us today.
Glad to be here. Thank you for inviting me.
Yeah, Chris has been involved in AM, I think, probably about as long as I've been involved in broadcasting. I don't know how long you've been in there, Chris, but somebody asked me one time, he said, "Boy, you've been in this business a long time." I said, "Yeah, I think the best I can remember, the first job I ever had was setting up a remote at the parting of the Red Sea." So you probably haven't been in there that long, but
No, 50 years this year, so
oh,
been,
really?
been a while.
Yeah, okay. Well, Chris, we want to talk about today things about AM and more particularly, and I know you've got some good information on various subjects concerning AM, but things have changed over the years about how you actually maintain and measure the power on an AM station. So I'll turn the program over to you, and if anybody has any questions, just enter them in the chat box, and we'll be glad to share them with Chris. Chris?
All right, let's see if I can get this thing shared. Is that working?
It's coming up. There you go.
All right. Yeah, I before I get started on this program, uh, let me address what you're talking about there. For many years, we always use the direct method of, uh, of power calculation. We would have either a base resistance or a common point resistance, a measured value, and then we would use an RF ammeter and just use the I squared R formula, and that would determine our operating power. And you can still do that. It's still in the rules. However, um, uh, quite a few years ago, and this really goes back, I think, to the late '80s. It's just been kind of ignored for by a lot of people just because they had always done it the other way. But the FCC will allow you to use essentially a transmitter power meter, that uses amplitude and phase to determine your forward and reflected power, and you can determine your operating power there. So that is in the rules. I I pretty much quit using I squared R a long time ago for these things. It's so much more convenient to just take the power reading right off the front of the transmitter. Take the sample out of the transmitter to your remote control, either an analog sample or else SNMP value, and just do it that way. So anyway, that's a good way to do it, and it really eliminates the need to run a wire out to a remote reading ammeter at the tower base or even a TCT in the phaser itself, where you would take a current sample. It's just so much easier to take a power indication off that. I put a program together here to just really take you guys through AM directional antennas. We're going to really focus on directionals today, although a lot of what we talk about also applies to non-directionals. This particular background shot that I'm showing you here is my 970 array in Buffalo, New York. It's a 5 kilowatt diplexed array. We own the site and we diplex with another station up there, and that's Lake Erie in the background. We were right on the shore there of Lake Erie. Anyway, it's kind of a good picture because it's probably the only one of the only uh, uh, directional array sites with a nice green mowed grass, where you can actually see the whole thing. Let's see if I can get this thing to advance. There we are. All right. Um, oops. There we go. I was trying to see if I could get my screen to do what I want it to do. Um, AM directionals are used to protect co and adjacent channel spectrum neighbors. They're used to direct the signal where you want it to go and to direct it away from where you don't want it to go. Primarily it's for spectrum protection, but if you're on the coast, why shoot a bunch of signal out into the Gulf or out into the Atlantic or the Pacific that you're just wasting? Save your power and send it where you want it. Uh, and so that's what you use directional antennas for. You define the pattern by a mathematical formula that essentially integrates the signal coming from all the towers in the array to land at a single point, and you integrate these complex voltages as they arrive from the tower. Um, and there's your formula. Hope everybody gets that. But the things that are involved in that are the power from each tower, the phase of the current in each tower, and then the space phasing of the distance between each tower. So there's multiple things that all come into play there, and they all add together to give you a vector sum at a given observation point. And you do this all the way around. And it's not just a two-dimensional thing, it's a three-dimensional exercise. The radiated field is determined at both a given azimuth and an elevation. So you're looking out and up. The vertical angle is usually only of interest for nighttime and critical hour modes, um, because that's where the ionosphere comes into play. Uh, but it's kind of hard to have a monitor point up in space. I guess now that we have drones, maybe we could do it, but who wants to work that hard, right? So we use monitor points on the ground that are related mathematically to that what the signal would be above the ground, and we can use that as an indicator of if things are working right or not. A couple of graphics here. This pattern that you see at the top right there is this is the daytime pattern of my 50 kilowatt Los Angeles station, 4 tower directional array. And anyway, it's a horizontal pattern. So on the ground, that's the shape of the pattern. Now, what is this silly looking green thing down underneath it? Well, I had this guy contact me. He was an engineer, and um, he was playing with 3D printing, and he said that he had come up with a program that would that would actually model and make a 3D model, 3D printed model of the hemispherical pattern, so both in the horizontal plane and the vertical plane. Now, that green thing at the bottom was the model he sent me of that same pattern, and you can actually see the height of it in addition to the girth of it. It's rotated differently than the graph up top, and I deliberately did that so you could actually see the backside of it, and you could see how that actually all pulls all the way down to zero, nearly right there in between the lobes at the center of the array. But you can see it's a three-dimensional exercise. The FCC licenses contain a couple of things. They have a set of theoretical parameters on there. The theoretical parameters are what you plug into that formula to determine the horizontal pattern, the shape, and the size that is. And it has a quadrature element in it, and it gives you a what they call a standard pattern, and it's the maximum that the signal can be in every direction. But then that'll be on the station license, and that's what everybody uses to determine what the shape and size of a pattern is. But there's also a set of operating parameters, and these generally differ from the theoretical because the operating parameters are determined during an array setup and proof. And what you're doing there is you're working the error vectors out of it. You're adjusting for a measured result on the ground that will yield the something that is within the parameters of the theoretical pattern. And these parameters, you've seen them on your licenses. They have a tower number, a current ratio, and a phase. Those are the three things for each tower, and for each pattern, for each tower and each pattern. Now, conventionally proofed arrays, they'll also have one or more monitor point descriptions and maxima. Typically, this is on each null radial. You'll have one. Uh, and if you've got one of those patterns that has a whole bunch of nulls in it, you may have a whole bunch of monitor points. And, the FCC rules say that we have to measure those uh, often enough that we can make sure that we don't exceed them. And it's kind of a double whammy there, and I'm sure Larry could speak to this. But if they catch you with the monitor point out of tolerance, then they can also get you for not measuring them often enough to keep them in tolerance. So you can actually get double dinged on something like that. But it's these operating parameters that the broadcast engineer is responsible for maintaining. We'll talk about conventional proofs. Arrays are, if you use a conventional proof, which is the way most arrays have been traditionally set up. They're initially adjusted by making field measurements on the ground along radial paths from the center of the array. So first thing you do is you take, and we're just taking a helicopter view of this. I'm not taking you deep into these procedures. I just want you to have a good understanding of how we get our operating parameters. So first you take a set of non-directional measurements using a single tower in the array as the radiator. It's usually the tower nearest the center of the array. Usually it's at 1 kilowatt of input power, but it can really be at any power. And you select that power. You generally want the maximum power you can get up to about 1 kilowatt that doesn't interfere with spectrum neighbors. So, if you've got somebody not too far away, a couple hundred miles away, you may be at 500 or 250 watts for these non-directional, so you're not interfering with them. And then you measure from very close in to this tower out to 3 kilometers at closely spaced intervals. How close do you start? You start as close as you can still get a reading on the FEM, on the field meter. So wherever the 10 volt point is. Right below that is usually the first point you're going to measure. And then you measure, in like 5 meter increments all the way out to 3 kilometers. And then you measure beyond 3 kilometers out to 25 or 30 at greater intervals, 1 or 2 or even 5 kilometers. And then you take these non-directional measurements and you plot them on log paper and you graphically analyze them to determine the inverse distance field or IDF along the radial. And here's an example of that. This is a radial I ran on a station in Colorado of ours. And you can see all of those close in points that I ran inside 3 kilometers there. And I analyzed that and came up with an IDF, a non-directional IDF, and this was at 500 watts, by the way, of 212 millivolts per meter. How did I wind up with that? Well, look at those points between about 0.3 and about 0.7 kilometers there, and you'll see they go right down that inverse distance line at 212. When you get inside of about zero point 0.3, you see some what they call proximity effect that you can get with the FEM, and that has to do with the current distribution on the tower uh, that can cause an error in your reading. And then once you get beyond about 0.7, now we start to see some scatter from ground conductivity, some dielectric, ground dielectric changes, and other things. And then as we go on out, all the way out to 33 kilometers or there, you really start to see the ground conductivity come into play. And I analyzed that at 15 millisiemens per meter there. So that's how I came up with the 212. Well, then you put the array in the directional mode, and then you repeat all those measurements beyond 3 kilometers. And then you ratio the directional to the non-directional at each of these points. And you take an average of the ratios on the radial. You can take the arithmetic or the logarithmic uh, ratio and then average it, but you have to stay consistent. So if you take the arithmetic ratio, you have to do it consistently, or logarithmic, you have to do them all that way. And just a word of warning, you'll get a lower number with the logarithmic ratio, but and that you think, well, that's good. I'll be lower on my null radials, and that's what I want. But you can get in trouble on the main lobe because you have to meet 85% of the standard pattern RMS. And so you can find yourself too low in the main lobe if you go logarithmic. So it's kind of a judgment call, and you may need to try it both ways just to see what works. Anyway, that average ratio, you then multiply it by the non-directional IDF, that 212 that I came up with, and that gives you the directional IDF for that radial. And then once all those radials have been measured and determined to be below the pattern maxima, one point is selected on each null radial as a monitor point, and then the maximum of that monitor point value, the limit that'll be on the license, is the radial maximum IDF, whatever the standard pattern value is, divided by the measured radial IDF times whatever that monitor point field was. Here's an example of that. This is that same radial, and you can see these are all the points beyond 3 kilometers. And you can see that I did 0.5 kilowatts non-directional. You got your dates and your times and all that. And then you see the directional millivolts per meter. And then over there in the far right column, you see the log ratio that I took. And then down at the bottom of that, you see the log average ratio is 0.1241 here. And then we multiply that times that 212 that I came up with. And that gives us a directional inverse distance field for that radial of 26.3. That's a good number because the maximum for that radial on the construction permit was 31.6. So I was at 83.3% of the maximum. That's a good place to be on that particular radial. Now, you'll notice if you look at point 3 back over there, I have MP. That's the point I selected for the monitor point. when I filed this. I picked it because it was an easy to get to place that we it was unlikely that it would be developed or become inaccessible. It was actually a gate to a farm field that had a little stub of asphalt you could actually pull in there and be off the highway, and it was a good spot. So I chose that point as the monitor point, and that's what showed up on the station license. The limit at that monitor point was that 31.6 maximum IDF divided by the measured 26.3 times the 23 millivolts that you see up there. Um, I'm sorry, I had that wrong. Times the 2.9 millivolts. That would be the limit. And I didn't work that out to tell you what it would be, but it would be a little over 3 millivolts per meter would be the limit for that monitor point, and that's what would be on the station license. Well, obviously, there's some problems with this method. Uh, One of the biggest problems is that you got to run an entire radio and do the averages to figure out what the maximum field at just one adjustment point on that radial is. And you see, when you're tuning one of these things up, you got to put a bunch of people with radios and field meters at 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 measurement points on each of these radials. And you need to know, how does that point that that guy is sitting at relate to the whole radial? Is it representative of the whole radial? Is it higher than the whole radial or lower? Where does its ratio work into the average? And so it takes a lot of measuring and figuring just to figure out if that, how that point relates to the radio. And then the next thing is, in almost all but inline arrays with an odd number of towers, that non-directional tower that you used is not in the center of the array. You got a parallelogram, if you got a rectangle array or what have you, then the non-directional tower is not really in the center of the array. So you got that offset error in your measurement geometry. A lot of things can influence the measured field at a given location too. Nearby re-radiating objects can influence the local field, and they can do this really without affecting the overall radial. And that's why we measure many points on a radial. You can't just go out and measure one point on each radial and adjust for that and call it good, because you can have significant errors at any given point. And then making measurements. It is time and effort and money and energy sapping. I mean, people used to ask, how much does it cost to tune up and proof an array? Is it 10,000? Is it 20? Is it 50? Is it 100? So you'll add all those together and you're probably getting close. Another thing is that these close in non-directional measurements inside 3 kilometers, they got to be made on foot. And when you're doing that, you got to deal with fences, ponds and lakes and rivers, terrain features, angry pets, livestock property owners. All of these can make these measurements hazardous. I could tell you stories about us doing walk-ins on these and crossing private property and running into different livestock and different property owners that were not happy. And technically, you should probably ask at each location, "Can I cross your land?" But if you did that, you'd never get the proof done. It's easier to ask forgiveness than permission. Here's a picture of this is Amanda, our chief engineer in Denver, um, and Todd Stickler, who is our engineer in Los Angeles. And they were doing a walk-in on a radial up there at one of our Southern California sites. And this is the kind of stuff they run into. They're having to walk through this to get these measurement points. And as you can see, it's not easy. In fact, just in front of Amanda right there, and right behind me, I took the picture, was a drop off, and it was like a 50-foot bluff. What are you going to do? Get out the rappelling gear? Well, I guess you are. This is the same area. You can see the array towers right behind it there, but you need some measurements out in there. Can you walk on water? I know one guy that could. It's not me. Well, let's talk about moment method proofs briefly. In 2007, the FCC began allowing licensees to make calibrated moment method models of their directional antennas and determine the operating parameters from those models. And you start with the set of base impedance matrix measurements. And that's a fancy term for measuring the impedance of all the towers with the towers in the same condition. So, for instance, you would, if let's say your towers are relatively short, they're let's just say 120 degrees or shorter, you would float all the towers, insulate them all, pull the J plugs at the tuning units, and then one at a time measure at that J plug the impedance of the tower. If the towers are taller than that, say 120 or more, you'd short all the towers and measure at the J plug for each tower all the way around. But the important thing is that you do them all the same. And then from that, you build a moment method model. And you can use you can use NEC. We were talking about NEC 5. You can use mini NEC. You can use any NEC program to construct and run a model for each tower. And of course, each tower's non-directional model has to have all the other towers in it because they all influence it. And you have to duplicate the conditions that you used when you made those matrix measurements. You also have to build a nodal circuit model to determine the effects of the base region reactances on the measured impedance. You've got a base insulator that's a big capacitor. You've got feed tubing that's an inductor. You have isocouplers that have capacitance to ground, Austin ring transformers, perhaps, lighting chokes, static drain chokes. Those kind of things are all a part of this circuit model, and they affect the measured resistance. And here's an example of that. This is a base region model I did on an array. You guys may have read in the trade press where I had a farmer pull a tower down at one of my Michigan tower sites. And anyway, after we got the new tower back up, I had to do a moment method model on the thing, and this was one of the calibration models. But you can see there the current source with the arrow pointing up. There's a resistor there between nodes 1 and 2. That's a 1 ohm resistor that I put in the model for the sole purpose of getting a measurement point, a node at node 2 to measure the impedance. Between 2 and 3, there is a coil. That's actually just the inductance of the feed tubing between the tuning unit and the tower. From 3 to ground, there's a capacitor. That's the base insulator. From 3 to ground's another capacitor. That's the Austin ring transformer. And then from 3 to ground, you see a resistor, and that is the modeled resistance and reactance of the tower base. In this case, if you look at the very bottom of the printout, it shows R 67.627 and 153.07. So that is the modeled impedance of the tower. If you look at the right side of the printout, there are some red numbers under 2 impedance, and you'll see it shows 71.41 plus J 163.105. That was the impedance on the other side there at node 2. And that was the effect that the series feed tubing and the base insulator and the Austin ring transformer all had on that modeled impedance. So you see it's substantial. It's about 4 ohms of resistance here and about 10 ohms of reactance, and we need to know about that. So we have to model that. What we have to do is make our model match the input impedance of this nodal model. So what we do is we adjust the height and radius of each tower in the model so that we get a match between what we measured and what that model showed within 2 ohms and 4%. Then we run a matrix inversion program, and that's some smoke and mirrors. It's a set of simultaneous equations that we run to determine the model source voltages and phases that it takes to produce the theoretical ratio and phase moments in all the towers. I have my own program that does this. I wrote it and I sell it. It's on the SPE website in the bookstore. There you can get it there if you're interested. It's called ACS Model, but it does all of this for you. Um, but it produces the correct source voltages and phases, and then you plug all of that in to a table and you determine the offsets that are produced by those base region reactances, and then from that you get the operating parameters. Now, if you're not base sampling, if you're loop sampling, there's another procedure that you use, and I won't go into that here, but it's another procedure that you still do all of everything I just said. You just look at a different place to get your currents and your phases at a certain elevation on all the towers to become your operating parameters. Here is an example, and this is that Michigan array. But just to quickly take you through it here, where it says peak current magnitude and current phase, those columns, those are the modeled currents, the magnitude and phase of the modeled currents from the moment method model. These next two columns, the W cap current offset and phase offset, those are the offsets produced by those base region reactances. And then those last two columns, that's what will be on the station license as the operating parameters for the array. So you can see tower 2 is the reference tower at 1 and 0, and the others are, you see the ratios and phases. In fact, this has all been granted. I got a grant a couple weeks ago on this, and that's exactly what is on the station license there.
Chris, the drawing that you showed earlier, that where you had an inductor, which was actually the feed point, and all the capacitance of the base insulator and all, how did you actually determine the values of those?
Well, there's a couple of different ways to do it. In this particular case, I had a manufacturer specified uh, capacitance for the base insulator because we had to buy a new base insulator from Austin Insulator for this tower. And so they gave me a value of 23 picofarads for that base insulator. And then for the Austin transformer, I had to buy a new one of those too. And they gave me a value of 27 picofarads. And so those are the numbers that I put in the model. Um, so the series feed to me, you can measure that. But you know what? The FCC allows you to go up to about 10 microhenry, so you can actually just fudge that to make it match. And that's usually what people will do. They will take assumed numbers that are reasonable for the base capacitor, the base insulator, sorry, um, and whatever else you have over there, and then they will just adjust that series reactance until that number matches the model. Does that answer that for you, Larry?
Yeah, I was just wondering, was there an actual, did you actually measure that, or was that something that came from the manufacturer?
Yeah, it's kind of hard to measure those real low values like that. They do it somehow. I don't know. Kentronics can do it too. I wouldn't even venture to do it. The capacitance in my test leads would be greater than anything. Would be greater than 23 picofarads. So I wouldn't even try. But generally speaking, those things are specified. So if you know what if your make and model of insulator, of transformer, of isocoupler, those should all be specs. All right. Well, anyway, so the moment method is a far better way of determining operating parameters. It eliminates all of those environmental effects that are beyond your control. It requires no repetitive field measurements, no close-in measurements, no angry landowners, no bulls chasing you through a field, no walking on water or rappelling down cliffs. It's great. There's no radial monitor points on the station license. And there's this philosophy. It's not in the rules, but this is we talked about this. I was on the committee when we put these. We worked with the FCC to draft these rules, and it's a clean site philosophy, and it applies in most cases. And what that means is this pattern is correct. And when it leaves my site, the radiation is the correct shape and size. And whatever happens to it after that is not my problem or responsibility because I have no control over it. And there's FCC rules in place. Ray Benedict worked very hard to with the committee, and I was part of that too, to get some rules in place to protect against pattern disturbances by construction or modification of nearby towers. So if anything that's FCC licensed or registered, they have to protect these moment method modeled and conventionally proofed arrays. But a lot of things, somebody puts up a water tower, you have no authority over that. The FCC has no authority over that. A utility company puts up a power line tower. That there's no way to stop any of that. Well, anyway, so let's talk about directional array maintenance and operation and so forth. These operating parameters have to be maintained within prescribed limits. You guys know this: 5% plus or minus 5% for the ratios, plus or minus 3 degrees for the phases. And if the array is conventionally proofed, it has monitor point fields values on the license, then you've got to maintain those fields below the specified maxima. Directional arrays, they do drift, some worse than others. Ground conditions can affect this, going from wet to dry, from frozen to thawed. They're prone to impact the self-impedance of the individual towers. And because of that, it affects the currents and the phases. I mean, uh, what is an impedance after all? It's the voltage to current ratio, right? So if you change the impedance, you change the voltage to current ratio. Um, Components are prone to change value with temperature. Mica capacitors are the worst. They're especially prone to value changes, and they are the number one leading cause of problems in directional arrays. I'll just go ahead and say that right out front here. Um, and anyway, uh, there's a lot of things that can cause you all kinds of problems here, that can influence the field at a monitor point. So let's just say you have a monitor point that goes high. A lot of those things are beyond the broadcaster's control. Um, Re-radiating objects, like we said, power line towers, water towers, wireless carrier monopoles, communication, broadcast towers. What about tall buildings? And again, if the re-radiating structure has an ASR or is the supporting structure for something with an FCC license on it, then that licensee has the responsibility for detuning that structure at its own expense. So they have to protect you. But what about these non-FCC licensed structures? The broadcaster is on his own, and you you're just out of luck there. You may, if you have a monitor point and it goes high, you may have to bear the cost of detuning. I just thought I'd show you this. This is kind of a neat graphic I put together years ago. This is a method of determining the amount of re-radiation from a potential re-radiator. So let's just say we have a directional array up there at the top where it says primary radiator, and then you have the re-radiator down at the bottom. Let's just say it's a monopole tower for Verizon Wireless. You draw a line between those 2 points, and at the center of that circle, that's the center of an arc. And you make a set of measurements around the bottom right quadrant of that arc, and you orient your meter. You use that electrostatic brake in the antenna. You see it says slot there. You use that like a gun sight, and you point it right at your array or your antenna. And what that does is that if you look at those dashed lines there, that puts the loop, um, the null right toward uh, your radiator, and it puts the loop right toward the re-radiator. So as you measure these points all around there, and you determine the distance, that's really all you care about is the distance and the field. And then you take those and you plot them on a piece of log paper, and then you analyze them just like I did that 212 paper we saw earlier, and you can determine the inverse distance, the re-radiated inverse distance field of that potential re-radiator. And if it's more than about 10% of your maximum for that particular radio, then you probably need to deal with that re-radiator and detune it. But anyway, that's how you determine that. So it's kind of a neat little exercise. Again, a lot of walking, a lot of driving, a lot of energy. Uh, I'm having trouble seeing some of my screen here because of the Zoom stuff on top of it here. Ah, there we go. Um, so you have to reduce um, the power to keep the monitor point fields below the maximum. You may need to get an STA to do this with the FCC. A lot of times the radiation will be local and it's affecting just the monitor point, but it's really not affecting the overall radial inverse distance fields. The only way to determine this is to essentially run a partial proof. If the overall average ratio, directional to non-directional, shows the radial inverse distance field to be below the standard pattern value, you may be able to change the limit or choose another radial point on the monitor point. Either way, it's a lot of work, it's a lot of paper, and a moment method modeled proof array has no monitor points or monitor point issues. I'm just saying. So anyway, a lot of advantages to that.
When
You
if
don't
you
deal.
have when you're using MOM and you don't have a, monitor point, how would you know if you had a problem out in the field of re-radiation?
I guess my question back to you, Larry, was why would you care? I mean, in the real world, unless it was somehow really impacting either you and your coverage, or you were getting a complaint from another station that interference was being caused, you wouldn't even care. I'll say this, and I've heard Ben Dawson say this too, that I have never seen that happen. I've never seen it happen since we have been doing moment method arrays. We've never heard of a station complaining of interference because of re-radiation that we didn't pick up on because we weren't, using a monitor point. So I just don't think it's an issue.
I
Uh,
guess quite often it doesn't really affect the whole radio. It just affects a particular monitor point.
that's correct. That's correct. You don't deal with this much in Alabama, but frozen ground, particularly in otherwise low conductivity areas, can have a much higher conductivity than thawed ground, and that can cause all your monitor point fields to go way up. You may have, like in Alabama, you got ones, one and a halves, fours, fives, pretty low conductivity values, and those can jump up to 30 if you get a hard freeze where the ground itself actually freezes. Uh, in some areas, it may be necessary to run a winter proof to get higher monitor point limits so you're not above the value all winter. I had to do this in Albany, New York. I had a 1540 50 kilowatt station up there, and every winter when the ground froze, all the monitor points would go high, and I had to reduce power, all winter. And so at some point, I said to our engineer, I said, put on your snowshoes and get out there and let's run a winter proof. And we did, and we got higher limits, and that took care of that. More likely in your part of the world, it's wet ground conditions, particularly in otherwise low conductivity areas, that can cause higher conductivity than dry ground and cause your monitor point fields to go up. It's not as drastic usually. As a rule, this has been my experience. wet, highly saturated ground will tend to go toward a conductivity value of 8. But you can see if you were at 4 to start with and you went to an 8, you could have double the field at a point. It would be pretty easy to do. Wet to dry can make a big difference. Every directional antenna and every pattern has a personality. And what I mean by that is it behaves in a certain way. It drifts in a certain way with temperature, it drifts in a certain way with conditions. It responds to phasor controls in a certain way. And a lot of times it's not like you would expect from the control function labels. Something that says tower 2 phase, you may adjust it and it has more effect on tower 2 ratio than phase. Um, each control will affect all the parameters to some degree, and how those parameters are affected is part of the array and pattern's personality. And this is important for the engineer that's maintaining these things to learn this personality, and then he can use that knowledge as he maintains and adjusts the array. For instance, if a clockwise adjustment of tower 1 power control causes the tower 1 ratio to increase, the tower 1 phase control to decrease, and then tower 2 and 3 to decrease, take that into account as you adjust the array. So, and that way you might want, along with turning the tower power control clockwise, maybe a tenth, you might want to preemptively bump tower 1 phase up a tenth and 2 and 3 power controls up a tenth as well. And you'll get really good at this after a while because you just know that when I turn this control this way, it's going to do this, that, and the other thing. And I can go ahead and compensate for that and make one adjustment, then look at the antenna monitor and, oh, look, it did exactly what I wanted it to do.
You
Let's
have to be careful when you do that too, Chris, that to go back and check the common point because that will actually could throw the common point off.
Well, that's the last thing you will always do. You will always end with an adjustment of the common point match so that you get back to 50 ohms J0. So yeah, always after any adjustment, go back and do that. So what do we do when things go wrong? And they will go wrong. First, stop and think through the symptoms and the indications. Get a good idea of what's going on here. You may very quickly, without doing anything else, come to some conclusion that's very valid. Um, do not ever, if you don't get anything else out of anything I tell you today, do not ever try to fix an array problem with phasor controls. Don't touch the phasor controls to fix an array problem. Figure out, is this a real problem or is this something with the sample system? Look at your common point impedance and current or your transmitter forward and reflected power. Are the parameters different than normal? Did they change? Did the resistance change? Do you have more reflected power now than you did before? Ask yourself those questions. If it didn't change, chances are you're looking at a sample problem and it's not a real issue. Are the parameters of more than one tower affected? Or, are they all affected? If it's just one tower that's affected, chances are you're dealing with a sample problem on that one tower. Because remember, this is a big series parallel circuit. Everything's coupled to everything else. You make a change anywhere, it changes things everywhere. So if you get a change on just one thing, one tower, then that's a good indication that you have a sample problem. Uh, if the common point impedance is normal, normally 50 ohms J0, and only one tower's parameters are impacted, look at that antenna monitor and sample system. And one thing you can do is you can swap the non-reference tower inputs to the monitor and see if the problem followed the sample or if it stayed with the antenna monitor channel. Of course, if all the parameters are off except the reference tower, then it's possible that the reference tower sample has got a problem. And of course, everything's referenced to that, so it's all off. And a good indication of that is look at the direction and the amount by which all the other samples are off. If all the phases shifted positive by 5 degrees, then chances are your reference tower actually shifted -5 degrees is what happened. Those are the kind of things you can do. Use a vector network analyzer if you have one. And I'm just going to say this here, everyone should have one to look at the sample lines. This particular, you think of vector network analyzer, you think, that's a $20,000 expense. I paid $115 for this one. This is called a Nano VNA. I got it on Amazon. And has in connectors. It comes with a calibration kit. And as far as I can tell, man, down especially at these AM frequencies, it is just dead on. Also, I used one to tune my 80 and 40 meter wire, and it worked good for that too. But for 115 bucks, pick one of these up on Amazon, and then you got it. For a little exercise for this presentation, um, I wanted to look at a line and show you guys how to do this. Uh, Here in this building, we're in a high rise. We're up on the top full floor. And when we built this place out, built the radio stations out over there, um, I ran, like any good ham operator, I ran an extra piece of RG8X up to the roof. You never know when you might need to do something like that, right? So that line's just sitting there. So I went over there and I connected up my little VNA to it. I ran a sweep from 500 kilohertz to 4.5 megahertz, and this Smith chart was the display. This came from the app, not the screen on the device. You plug a notebook into it, and you get a lot more information. And you can see the little red marker there. That that is 1.1 megahertz is what that showed up as. The green one to the right of it, the next trip around the circle, was 3.3 megahertz. That's a roughly 3-to-1 ratio. So that tells me that these are open. This line is open on the far end, by the way. So it's an open circuit. That tells me that the first one, the red one, is a quarter wave. The green one, the second trip around, is 3/4 wave resonant point. And so you can tell by the mathematical ratio, it's 3-to-1 ratio. And so I was able to figure this out. You see my math over here to the left. The quarter wave was 1.0147 megahertz. You multiply that times 4, and you come out with 4.0588 megahertz. You plug that into your formula, 984 divided by that, and it gave me 242 feet of electrical length. And the velocity factor specified for this Belden RG8X was 0.82. So my physical length was 198 feet. That's about what I thought it was, 200 feet of line going to the roof. Then we can take an impedance measurement at plus and minus 45 electrical degrees from any resonant point. And then we take the arithmetic mean of those 2 points, and we can determine the uh, characteristic impedance of that line. And so I shot one at 225 degrees, which was 2.8 megahertz, and one at 315, which was 3.9. You can see the R and the X there that I measured for each, and then the magnitude. And so I determined through using my formula printed up there at the top that the operating impedance of that line, characteristic impedance, was 48.9 ohms. That's pretty reasonable for a 50 ohm piece of RG 8X. So that was just a quick example just to kind of show you guys how to do that. You could do that same thing on a sample line, and you could tell in a hurry if it's the right length and if the characteristic impedance is right or whatever. You could also connect one of these things up to a line that's terminated into your sample transformer. Just do it on one frequency, and you should see a 50 ohms out there. Uh, there's a 50 ohm terminating resistor in the sample transformer, and that's what you should see out there. If you had a line problem, you wouldn't have this really nice spiral plot. You would be irregular. If it had more loss, then it would tighten up. You could tell in a hurry. And by the way, this little VNA, I haven't tried it yet. It has a TDR function in it. It could very possibly help you find a fault if you had it. So if you don't have a VNA, get one. But you can also use an ohm meter. It's not as utile, but it should show a low resistance plus the ohmic resistance of the sample line in most cases. If you're looking at a sample transformer terminated line, sample loop should show a short plus whatever the ohmic resistance of the sample line and isocoil. And then, of course, disconnect those things at the far end and make sure the sample line shows open. So just some simple troubleshooting things there. Uh, then isolate the issue to one pattern or the other. Is this array whacked out on just the day pattern or just the night pattern or both? If it's on both, then look for something that's common to both patterns, like the transmission lines, things like that. Visually inspect the phaser and ATU components. Look for swelling, cracks, seepage, and other issues in mica capacitors. Most of the time, maybe I don't want to go that far. Probably half the time, mica capacitor gives it up. It's going to puke all over the place. It's going to have solder and black tar and goop all over, and you got a big mess to clean up. It's obvious. Other times, it'll just be a little crack in the envelope of the capacitor. And so you may what you really need to do is like run a fingernail around the outside and see if you feel any cracks or what have you, any little bulges, anything like that. Um, Look for discoloration in coils, especially where the coil clips attach. I'm going to show you a picture here in just a few minutes of that. Rock those coil clips back and forth to ensure a good connection. Mark them where they are, pull them off, squeeze them together, put them back on. Make sure you've got a really good connection. Check all your hardware for tightness. Every screw, every nut, make sure they're good and tight. Wiggle all the straps, and where they connect, be sure that they are good and tight. If multiple patterns are affected, look at the tower bases. Look for foreign objects in the base insulator and stuff like that. Here a few months ago, Amanda, our chief engineer here in Denver, she told me that the KLZ two-tower array was totally whacked, and she was at reduced power. She asked if I'd go out and help her figure it out. So I went out there with her, and it's just one pattern, but we have a non-directional mode for the two towers individually. So we put it on the west tower and it ran fine. We put it on the east tower and the transmitter wouldn't stay on. So we went back out there to the east tower and looked, and it didn't take but a second to find it. A piece of braid that attached that grounded, that's supposed to ground the Austin ring primary to the ground strap had broken loose at the solder point, and the wind had wrapped it around the feed tubing to the tower and shorted out the tower. I got a stick, reached out and flipped it off of there, and the array came right back to normal. That's the kind of thing that you look for if it's affecting everything. Look up the tower. Look for broken guy insulators, evidence of corona, carbon tracks on fiberglass rods, things like that. If you have a broken guy insulator, compression insulator, the two loops of the guy wire will short together. And if that's the one right up against the tower, you just added some top or center loading to your tower, and that's going to screw it all up. Look at these pictures. This picture right here. This came off of our 740 array in Los Angeles. One day that array just went whacked, and went out there with a impedance bridge and measured the towers. And this one tower, tower three, was just a few ohms. I mean, it should have been 30 some odd ohms, and it's down, 3 or 4 ohms. So we knew something was wrong, and we couldn't find any, and it was above the base insulator. So I sent a tower crew up there, and didn't take them long to find it. We had a corona event, and you can see that top fiberglass rod there, insulator rod. Corona had completely just blistered the outer fiberglass, delaminated it. And you could take an ohm meter and put across the clevis on both ends of that, and that's about a 2 ohm resistor there. That's how bad that is. That black is all just carbon. If you can look closely at the other two, and you'll see some tracks, some black tracks starting to go down them. That's where corona was starting to go down there. Uh, I had to. How did I fix it? First of all, I doubled up these rods. I went to a pair of twos, 2 footers, at each location against the tower. And then I put a corona ring on the clevis up against the tower, and that took care of that. Why did we have corona on this? Well, it was a combination of 50,000 watts of RF energy plus, 60, 70, 80 mile an hour Santa Ana winds blowing a bunch of super dry air molecules across the tower, giving up a bunch of electrons, and your corona. And that's what caused that. So you can use a drone if you have one and a Part 107 license to go up and have a better look at fiberglass rods and insulators. Check the temperature of your phaser and ATU components. Turn the array on and run it at whatever power it'll run at for a few minutes, and then use an IR thermometer to check these components for heating and for hot spots. Or if you've got one of those thermal adapters for your phone camera, you can do that and actually look at a thermal image, and you can see these hot spots if there are any. If you don't have any of that, just run it for a few minutes, shut it off, and then carefully feel of all the components for heat. Warm is okay, hot is not. A hot component is dissipating a significant amount of power, and that is ungood. Investigate the cause and fix it if you can. Loose connection, corrosion, whatever, and replace hot components for which an external cause is not apparent. Um, Check your transmission lines with a VNA or bridge, just like I showed you a few minutes ago. Identify and fix the issue, and then, and only then, touch up the phaser controls. I want to leave you with a few tips and tricks here, just a couple of minutes, and then we'll wrap this up. Watch for seasonal variations requiring adjustments that don't go back to the previous values or the settings as the seasons change. And this can indicate that you've got a component that's failing or changing value, and it can really give you a leg up on something like that. Here's another thing that I was taught many years ago. With everything working and the array adjusted for license parameters, shut the station off, go pull the J plugs on all the towers, and then measure with the bridge or a vector network analyzer, measure and record the static impedances of each branch. I'd measure at the output of each branch of the power divider. I'd measure at the input to each transmission line at the phaser. I'd measure at the input to each ATU. And you write all of that down and keep it handy. Then when you have an array problem and you can't find anything through all this other stuff, then go back and remeasure these points. And the place where you see the biggest change is going to be the branch where your problem is. And that'll really help you zoom in on it. ATU components live in a hostile environment, and keeping them clean and free of all the junk is critical to reliable operations. Coil clips, particularly on these ribbon coils, they can develop a series resistance and intermittent connections. So like I said before, regularly check them, rock them back and forth, pull them off, squeeze them together, make a tighter connection. Tarnex is your friend. Use Tarnex, and then be sure you clean it good after, rinse it good after you clean it. You don't want to leave the Tarnex on there, but you can get rid of the tarnish so you get a really good connection there. Although silver oxide is a pretty good conductor in itself, but it may not be as good as the silver. Pattern switching is a perpetual problem in many arrays, going from day to night or day to critical or DA to non-D. Solenoids and micro switches, they fail, they become intermittent. Keep some spares on hand. By the way, Kintronics, RF contactors, they use 4 different mounted micro switches. The micro switches themselves are all the same, but they're riveted to a Z bracket, and each one has a stamp number on it, 1, 2, 3, or 4. And you got to replace a 1 with a 1 and a 2 with a 2, etc. So get a full set or 2 sets of spares from Kintronics, keep them on hand, And then when you have a failure of one of these things, you can just simply swap that whole thing out very quickly. And the same would be true for solenoids. Keep some spare solenoids on hand. Keep a couple of them on hand. You can swap them out in a hurry. Porcelain insulators are prone to crack or break as a result of temperature swings, wind, and seismic activity. So check them, look for evidence of cracking and breakage, and keep a stock of spares on hand. They're cheap. Show you this picture here. This is one of the towers at our Southern California, Los Angeles 50,000 watt array. And I just showed you this picture because this is what an antenna tuning unit ought to look like. And by the way, we built this in 2012. I think this picture was taken last September. So that's what this thing looks at after it being out there for 13 years operating. It still looks this good. And I know you guys in Alabama are all saying, yeah, well, you don't have humidity out there. And you're right. We don't have the humidity to deal with out there. It's all pretty dry. And so you don't get the tarnish and things like that. But you notice there's no bugs, there's no snake skins in there or mouse nests. Keep it really good and clean. A couple of things to show you here on the left. Look at that. Under that ball gap there is a broken ceramic insulator. They picked up on this during a regular inspection back in September at that site. That particular side of the ball gap was being held in place only by the 3/8 tubing that you see at the top there, and could very easily have just shorted out the tower. What broke it? I'm guessing it was seismic activity. We get a lot of timblers out there, and they probably got one. It shook things up a little bit and cracked, and it broke. They found actually several broken insulators, but that was just one of them. And they had spares, and they replaced it, and all was good. This picture on the right of a 20 amp coil, and one of the things you can see discoloration, darkening of the silver plating above, below, and on either side of that coil clip. What does that tell you? That tells you that coil clip connection has been hot. And that's the kind of thing I'm telling you to look for and fix it. Tarnex is your friend. Squeeze that thing together, make sure it's good. We've checked. They did all of that, checked it, and the temperature is good and it's uniform. So that's all good. Pay attention to grounding. Look for signs of tampering or theft of your ground system. I swear, we get up there. We used to get up there to Red Mountain, go up there on top there to our FM site, and first thing you look at is the ground block. Is it there? Is it not there? About half the time somebody stole it. At an AM site, you should not be able to see radial disturbances in the ground. If disturbances are visible, like you see in this photo here, somebody may have stolen your ground system. Amanda took this picture years ago at a site, one of our sites in Denver. She had a pattern go out of whack. She went out there to look at it. Here's what she found. Evidently, they pulled up to the tower base. It kicked through the base fence. They dug around till they found where the radials attached to the ground ring there, pulled them up. As far as I can tell, they wrapped them around probably a trailer hitch ball on a vehicle and just drove and pulled those radials right out of the ground. They probably got $100 worth of beer and meth money, and it cost us $30,000 to replace this thing, to get this ground system back in shape again. How did I fix it and keep it from happening again? Couple things. We replaced it, and then I put 3 inches of asphalt on top of the ground screen, so there's no longer a place where anybody can get to many radials with one grab. And we caught this guy, and he went to prison. He was also stealing from an electrical contractor, and that guy put a game camera out there, caught his face. Channel 9 put it up with the story, "Have you seen this guy?" And he, believe it or not, he turned himself in. So we haven't had any more issues out there. But you go out to a site, and unless it's a new site, if they just put in and you still have the radial scars, if you see this kind of thing, you got a problem. And the last slide here, radial ground systems. They don't often make good lightning grounds. You're in shallow soil and limited contact with the dirt. Um, you need a good ground for lightning dissipation. Make sure you have an array of ground rods, at least four, around each tower base. And you connect them with heavy gauge conductors, 1/0 is what I like to use. CAD weld, exothermically weld those connections to the rod tops and connect to the ground side of the ball and horn arc gaps and ATUs. So when you take a lightning hit, it jumps those gaps and it goes straight into the dirt and not through your antenna tuning unit and transmission line and phaser. Finally, keep good records. Man, write down all your maintenance and repair activities so you have a record and know what you did. And this next part is really important. Note the dial counter indications on your phaser. Keep it in a table, and then you can track changes and you can notice, over time, I'm going out there and I keep turning this one control clockwise, clockwise, clockwise. What's going on? Well, a component's changing value. And then keep track of seasonal parameter shifts and required actions. That's it, folks. I don't have
Yeah.
much voice left. I'm about talked out here. So
Yeah,
I'm open to any questions or other discussions.
that's some excellent information there, Chris. I appreciate you doing that. Anybody have any questions, you could either open up your mic and ask Chris or pop something up on the chat menu. But I think the one of the things you touched on, I think is very important. Learn to look visually. Most of the problems you'll find, or you can find them visually. You don't, like you say, you don't go in there and start turning knobs. You just go around and look at everything. I knew Jeff Weldon, who both of us know, told the story about going out to a three-tower array and the transmitter wouldn't stay on. And he goes down and he says, "Well, let's go down and let's look at the ATUs." So they go down and open up number one, and it's fine. He doesn't see anything problem. Go down to number two, open that up, clean, no problem there. He opened up ATU number three, and there was a big snake coiled up in there. And this is a 50 kilowatt. He said, "Okay, we can fix that." So he closed it up and went back up to the transmitter and hit the plate on. Cha-ching, ching. Hit plate on, cha-ching plug. Hit it the third time, cha-ching plug. Then he told the other guy, said, "Now go down there and clean that snake out." So look, when you have a problem, take time to walk around and look at everything, and that will actually go a long way. We do have one question come up on the chat. Let's see what that is.
I'm looking for the answer to that right now.
Okay.
Give me just a second. Hopefully, I can actually find that. It's in part 73, subpart A, and determining operating power, 73.51 is your rule.
Oh
Uh,
yeah, right, right.
73.51.
That'll do it. Well, Chris, I sure appreciate your time today. That was a lot of good information. And, the new guys coming into the business, they don't particularly fond of AM and they despise directional AMs. But you and I both have been around a long time, and I really like AM, and I have a lot of fun with directionals because you get to do something. As Frank Jardina says from time to time, he says, "In an FM, a rigger puts the antenna on the tower and he's gone, and that's the last you see of it. But in AM, and especially in AM directional, you get to do something, change
Right.
things." So thanks for your time, Chris. That was most interesting, and I'm sure everybody got a good some good information from you and can go back and work on their arrays and make sure everything is okay. So with that, we'll end our webinar for today. Our next let's walk over here just a second. Here's our YouTube site. This particular webinar we did today has been recorded and it will be available in the next couple of days up on our YouTube site, as well as all the other webinars we've done over the years are available there at on the YouTube site. You can just go to YouTube and type in ABA engineering, and it will take you to that particular site. And our next webinar will actually be on March 17th. So make a note on your calendar to join us for that, and we'll be publicizing information about our guests at that time. So thank everybody for joining, and Chris, we appreciate your time and effort that you put out to put this webinar together, and we look forward to seeing everybody in March.